Hi everyone. Boy Christmas Pen is my name, and I'm here to present to defend the topic about tourism, transport intelligent simulator for forecasting tourism demand. Um, First of all, the background and introduction of our topic is states that tourism is one of main economic activities, and it contributes to the global and local economies GDP, creating jobs and then infrastructure development as well. And it's vulnerable to situations such as economic shifts, political instabilities, environmental changes, and global events which make it essential to forecast. The main objectives of our project here, we're looking at developing an intelligent simulator that is to forecast tourism demand, explainability of our model for transparency purposes, then implementing simulation to forecast tourism demand. So that is just basically to bring in simulation into play. Then adaptability purposes of evaluation in various environmental dynamic environments to ease the decision-making processes of stakeholders. Then going to our literature review, we're looking at cloud-based real-time tourism demand forecasting using deep learning approaches. One paper that was reviewed by Zhang, that was written by Zhang, and the computational problem here was there's need for real-time forecasting solutions to enable timely operational decisions and planning. And he suggested a solution which was to develop a cloud-based architecture using LSTM for real-time scalable, accurate, and for tourism demand forecasting. Limitations of this project were the inability or the insufficient or limited high frequency limitation to high frequency data, lack of integration of offline data sources, which could provide a holistic overview. Many among those, I'll not go through all of these, but then slides will be available. Um, Going to our computational problem, the pressing point here is that traditional models usually struggle with complex interactions among influencing factors, uh, which results into inaccurate predictions that lead to poor decision making and financial losses for stakeholders. And the limitations in the traditional methods are basically that they are limited to univariate time series data, which makes it difficult to capture influence of other factors on tourism. Hence, inaccurate predictions. And then this informs the data complexity and application data. The patterns in multivariate datasets are not easily utilized or not easily captured with the existing models, which calls for need for precision. Precision is accurate prediction, which could directly inform effective resource allocation, strategic marketing, and infrastructure development. Our proposed solution, as I said earlier in our objectives, is to develop an intelligent AI simulator that is to use machine learning and simulation techniques. The features in this case, we are looking at multivariate data analysis, scenario analysis using the simulation, then real-time predictions as well, then seamless integration of via API development. Um, the forecasting, we are looking at ARIMA, that is to handle the time series data, as well as the profit model. We also look at the random forest regressor, the gradient boosting models, as our machine learning models still to inform forecasting. The simulation environment, we are leveraging the SimPy technology. Later on, you'll also see that we try to implement the digital twin. Evaluation metrics still remain informed, where we have the mean absolute error, root mean square error, and then R squared. The novelty of our proposed solution, we are looking at XAI techniques, that is to inform of the transparency, which informs the trustworthiness in the state of the project. Then intelligent AI simulator, that is to forecast tourism demand, since we are going to leverage already trained models. Then simulation environment, basically for scenario analysis. Then accessibility using API is to inform seamless integration and distribution. Going to our dataset description, it was collected over a period of 10 years with entrance total rows of 3,653. It four target variables which were represented as companies, that one offering accommodation, two were for transportation, and the other were for the leisure facilities. Then we had 562 columns in total, together with the target variables. uh, accounted to 556. Then target variables I said earlier on. The features in the dataset were covering calendar effects, weather, and events data, basically. The missing values in that target variable, you had transport had 12 missing values, and then in knowledge you had 42, but all these were valued in an input mask, so you had to just use them in the preprocessing stages. Data types, we had integer data types, the data was all integer. Then went on to visualize some of the values, the columns, where I had a normal distribution for accommodation, which was also used as our target variable here. We had a normal distribution that whereby values were centered around the mean. And the other for the other target variable transport values are skewed towards the left. Values are skewed towards the right rather to the right. And then you have a great distribution on the left around the value of 200 and the frequency of 280. Then our correlation heat map for the for the data set, since we had four target variables, we established correlation around the two. A heat map basically shows the strength of correlation or influence or interaction using the power of colors. Mm, the dark red indicates a strong positive correlation, which is usually self-correlation. The deep blue is for strong negative correlation. Then the black is indicating no correlation at all. Then we have a strong positive correlation of 0.75 between temperature and transport, which informs that high temperatures greatly influence the choice of transport one. And a strong minus 0.01 negative correlation between accommodation and wind. Wind does not greatly influence the choice of accommodation. Then minus 0.46, which is a negative correlation between indoor leisure activities and temperature. Then coming to our methodology, we look at right away from the time we started, we collected our data, we downloaded the dataset from the Swiss platform, and this dataset underwent pre-processing. Since we said we had missing values, we imputed the missing values in other columns using the main, and then for the other target variables, since we had them in an input mask, we just had to ship them this side. Then under ADA, we went on to do the visualization whereby we came up with different graphical representation, the histograms, the EDA, the scatter plots, and then the pair plots as well. Then from that, we went on to do machine learning or predictive analysis, predictive modeling, where we developed quite a number of the machine learning models. And during this process of model development, we implemented the models, went through training, then evaluation. After model evaluation, using metrics of mean squared error, root squared error, and root squared mean error. Yes. We also wanted to do hyperparameter tuning, and after which we wanted to perform explainability. After explainability and understanding the features that went on to that contribute greatly to the feature out to the model output, we are to use them to inform our simulator that we are to implement using SimPy, and as well as implement a digital twin. Now, these features are the ones that are to serve as the inputs into our simulator. Afterwards, we implement the UI since it has to allow for interaction with the stakeholders, then API development for purposes of seamless integration, then product deployment to make it accessible through different platforms or networks. Some of the results, we implemented XGBoost, the linear regressor, the random forest regressor, decision tree, and the prophet model. But then throughout this, we observed that linear regressor had the fairest, or had the best performance, let's to say, of a mean squared error of 17.5799035, then and a root mean squared error of 21.88 The result of the ARIMA model, that is 200 time series data, we observe by the look of things, it is the manually trained model. We had both the manually and the automatically generated model. Whereby the manually trained had a better performance due to the fact that you had a perfect selection of the PQR, the parameters of the autoregressor, the integrator, and then the moving average. And even from the plot of the residues, we see a clear trend and implication that there was proper picking of the patterns of the interactions in and during the learning or the training of the model. Then the density of the residues, we are seeing them being skewed to the left, skewed to the right, rather. Yeah, they are skewed to the right. So they are having a normal distribution spread around the mean. Explainability, that is for purposes of transparency of the model and meeting standards, we use the local explainer and sharp. Local explainer, it explains why or the influence of a particular value towards model output. And then the graph itself, it has the y-axis, which has the features, and the x-axis, which has the line values. So we see that values of temp, holiday, and weather, they have a great positive impact on model towards model output, unlike temperature, which has a great negative, a less negative rather, then local event, vacation period, then sunshine, precipitation, wind has no contribution towards that. Then for sharp, sharp is a global explainer. It explains the interaction between all elements towards model output, whereby pink indicates a high contribution and blue rather indicates a low contribution, and we are seeing a high contribution provided by things like holiday, this is in pink, temperature as well, though it also influences, it has a negative influence and over great magnitude. Then external event usually it has the lowest because it is entirely blue. There's no interaction there. Thank you. Then moving on to our simulation, I think these are some of the papers that inform the simulation strictly. And then again, I'll deep dive into the methodology, but then it is an overview covering for both the simulation and then the digital twin, which starts with data integration. Since we already had the data set, we picked it already, we processed it already, and then we also implemented the machine learning model. So here we just ship them here, the data integration process, which we loaded the data set into the environment that we are going to run our simulation in. Then we also loaded the pre-trained models using the joblib5, joblib library. Then we use the ARIMA model, which is for time forecasting, to establish the baseline for the prediction or establishing the time. Then we also went on to update or updating the features, whereby these features were being sampled directly from the dataset to inform the real-time updating of the inputs. So it was sampled directly from the dataset. Then after that, we went on to adjust the forecast or to make the predictions using our linear regression model, which also imported as a pico file using the joblib library. Then after running the simulation, we logged outputs that would show the predicted outcomes of that. Then perform the what if scenario, where this involves feature manipulation, which involves increasing a particular value and then dropping the other to see the results or the return on the return of the simulation. Then I also went on to do evaluation of this. The workflow real basically it flows through those processes that I've been talking about. So it starts with a feature sampling, whereby the real-time updates of the features, for example, the temperature, the precipitation, and the local events, remember they are being sampled directly from the dataset. Then the baseline forecasting to establish the time. Then demand adjustment demand adjustment, which is performed the linear regression after sampling of the values from the dataset. Then we also went on to perform scenario analysis. So this is how it works, it runs through. Then evaluation as well. Likewise, the digital twin. Yeah, the digital twin literally also works in the same process, whereby when we initialize the digital twin, created using a real-time virtual replica to resume demand. So we also observe dynamic feature update, whereby we are sampling information from the dataset. I chose to do this simply because I wanted coherence in my work to make sure things are interconnected or are linked. Then baseline forecasting to establish the time. Then demand refinement or prediction is by the linear regression model. Remember, I chose it from the dataset because of the good performance that it had. Then scenario validation or performing the what if scenario analysis, then evaluation. I'll walk you through the code briefly after this. Then some of the results are the same pi and then the digital twin, but the digital twin was outperformed the SimPy simulation tool, and then we have a graph indicating the trend or the results or the predictions from the simulation tool that I implemented, whereby the blue reflects the forecasted demand with by the model, then the actual demand is reflected in the red dots on the ground, and both of them are fluctuating, though peaking at different values. Yeah, but then it is literally a real, rather a kind of a uniform trend, but then they're all fluctuating with peaks of about 100 in a predicted value, and then the actual value peaks, you're observing peaks of about 60 or 59. Yeah. Then for the digital twin, the actual prediction still they're also moving in the same wavy form with different peaks, but whereby the predicted is at 90 the digital twin, whereby the maximum prediction here and the actual demand is at 60. This informs some bit of connectivity together from the simulation twin and the digital twin, whereby there's a constant or there's a uniform way these guys are performing both together. Then feature importance, basically this is to inform what features influence the digital twins performance, whereby this informs us from this field goes back to the values we had during our explainability, whereby we have holidays, local events, and temperature, then wind still having a positive contribution towards the simulation's performance. And then weather summary, category, and vacation periods, they have a negative contribution, unlike precipitation, external events, and sunshine, which have none or a negligible contributions, their values at 0. Then for the simulation bit or the contributions in this project, really, I see the new thing we've implemented is integration of the ARIMA and the linear regressor models, basically for adaptive forecasting in the simulation and the digital twin. Then we also observe real-time updates of features whereby we are directly sourcing them from the dataset, which has not been replaced here. Then implementing of what-if scenarios. Then hybrid framework. Yeah, combining the SimPy and the digital twin technology kind of merges the two. Then implication of the project or kind of effects that we're looking forward at improving the tourism demand forecasting accuracy, then enabling real-time decisions based on the predicted values, then providing insights that are to handle extreme scenarios, and then showing potential use of this same technology in other sectors, for example, supply chain management. Then the challenges in this case, remember, the models were not having a good performance simply because one, the dataset was too big and then it had very many missing values. And we chose to just input them. An implication that the data quality was not that good. If at all, it had a big range of missing value. Then model generalization now, with the issues of what if scenarios, the model was struggling to still make accurate predictions. Then computational complexity. With some tools I try to implement and then still things were not working out due to the resources. So it wasn't a good thing to deal with. Then real-time adaptability. Yeah, there are some conditions that don't exist within this our own country setting like Uganda. So that becomes a problem. So real-time adaptability might be purposeful for this case. Conclusively, by use of this, we shall have an improvement in tourism demand forecasting using our technology. Then SimPy and Digital Twin really enable real-time and dynamic insights. They do provide those. Then scenario testing, which supports proactive decision making. Proactive is something taking action before something really happening. Then method, we can go on and adapt this technology in other industries. Yeah, that's all I had for today. Thank you so much.